Okay guys, for today's lesson what I'm going to do is I'm going to kind of talk you through number 1 and number 2. I really wish we were all here together and you could talk yourselves through it and I could just give you a little bit of help. But we'll go with this method for today. So let's take a look at number 1 on today's examples. It says the center field fence of a ballpark is 10 feet high and 400 feet from home plate. The baseball is hit 3 feet above the ground. It leaves the bat at an angle of theta. So they're not actually giving us the angle. They just say theta. With the horizontal and at a speed of 100 miles per hour. So we have a lot of things that we need. But what we have to do is we have to do a little bit of conversion here. So we have miles per hour and then we have feet and feet. So we're going to have to convert that miles per hour into feet per second is generally what we're working with here. So we're just going to take that 100 mph, miles per hour, and then we're going to multiply that with the 5,280 feet that are in 1 mile. And then we're going to multiply that times, we need per second. So we're going to change our hours into seconds. So there are 60 times 60, 3,600 seconds in 1 hour. Okay, probably would have helped if I had written this as miles over hours so you could see everything cancel. So I'll go back and correct that. And now we can see that the hours cancels with hours, the miles with miles, and for our units we're left with feet per second. Okay, so this is going to give us approximately 146.6, repeating, well that's more exact, but we're going to round in a minute, so feet per second. All right, so that's what we need to help us set up our parametric equations to represent this situation. Mr. Campbell does a great job of drawing, but I'll try to do a job of drawing and we'll see how it turns out. So if we have our field down here and the ball is 3 feet, okay, we're already kind of off scale here, 3 feet, and here's my bat. All right, that's a bat. And we're going to hit this and it's got to go, it's going 100 miles per hour. And we have to go 400 feet. And we know that this wall is 10 feet tall. All right, so obviously not drawn to scale in a lot of different ways, but we have our 10-foot high wall. We kind of have an idea of what's going on there. All right, so we have to represent it 2 ways. So we are going to represent that horizontal change with respect to time, and that would be that initial velocity of 446, and let's just say for the sake we're going to round this to the nearest thousandths, and that would be cosine of theta. We don't know theta. All right, times time, and then we have that vertical component. All right, so how does the height change in this problem? It is the negative 16t squared because we're dealing with feet per second here, so we're going to go with that unit, plus the 146.667 sine of theta, and then finally plus 3 because we're hitting the ball at 3 feet off the air. So that is our set of parametric equations that models this situation. So in this situation in B, if theta is 15 degrees, will the ball clear the fence? Okay, so how can we do that? Well, we can figure out what is the time it takes it to get to the fence, and then how high would it be? So to determine that, what we would do is we would plug in 400 feet, because that's how far away the fence is from where the ball is when it's hit, equals the 146.667 cosine of, this time they gave us 15 degrees, times t. We're going to solve for t. So t, when we take the 400 and divide it by this, t is approximately 2.82 seconds. So that gives us the time that it would take this ball to get to the wall. Now we can figure out the height of this by plugging in that 2.28 into the height equation. And so it would go in here, negative 16, 2.82, squared, plus the 146.667, sine of 15, close your parentheses right here, times the 2.82, and then plus 3. And so what we're going to find is that 2.8 seconds later, our ball would be at negative 17.19 feet. All right. Okay, so that's not really a possibility. That's telling us it's down here somewhere. It went underground. So what that probably means is the ball hit the ground someplace before it got to that 10-foot wall. So no, our ball is not clearing the fence. It definitely wasn't high enough. We got a value that's actually not even a possibility, probably because that curve would have, that height would have told us we're down here, so it would have hit sooner. All right, what about 23 degrees? So we pretty much go through the same process for 23 degrees. We would go back to that initial equation, the 400 equal to the 146.667, but this time we do cosine of 23 degrees, so we're really just changing our launch angle, and when we do, it changes the time that it takes us to get to the wall. So now we're going to get there in 2.96 seconds, and then when we plug this in, y of 2.96, we get negative 16 times 2.96 squared plus 146.667 sine of, we're changing our launch angle, so that changes here as well. Our t, we just figured out, it's not t anymore, is that 2.96 plus 3. And so this gives us approximately 32.44 feet. So in this case, we are above the wall. The wall is 10 feet high. We are at 32.4. So this would be a yes. And then D, what is the minimum angle required for the hit to be a home run? So what we want is we want to find out where this part is greater than 10. So this is what we need. We need this part of the equation, the height, sine of theta plus 3 to be greater than 10. So the first thing we'd have to do is we have to take this part that we know, and we're going to solve for t. So we have 400 equals 146.667 cosine of theta, which we don't know, times t. And we're going to solve for t. And when we do, we get 400 divided by 146.667 cosine of theta is t. So where t is, whoops, there should be a t right there in our equation. Where t is here and here, we would have to plug in this guy. So right here where t is, and right here where t is. So we get negative 16. Then we have 400 over 146.664 cosine of theta squared plus 146.667 sine theta times 400 over 146.667 cosine theta plus 3. Okay, so before I go any further, I want to talk about this little piece right here. This and this will cancel. And then what we have is sine over cosine, which is tangent. So this piece does not simplify very well. We'll leave that guy alone. We're going to use Desmos in just a second to clear this up, so we don't have to worry about that too much. This becomes 400 times tangent of theta, because sine over cosine is just tangent. And one little last piece that I didn't show a second ago, we're going to subtract the 10. So we're going to get a -7 right here. And now we just want to know where this is greater than 0. So we can now take this portion, this part, plug that into Desmos, and look at where does it cross that x-axis, because that is the angle that will give us what we need. So let's go into Desmos. Be patient with me just for a second because I don't think I have it opened. We will open a new window. Go into Desmos, type that in, and see what we get. All right, so our equation was y equals. This is -16. All right, this is going to be a little crazy, but we can type this in, no issues. We're going to go open our parentheses, and we're going to tell it, we're going to do division here in just a second. Okay, and this is 146.667 cosine, go find cosine, and of x, and all this was, whoops, squared. Let's go back. I'm going to go out here so I could square that. All right, and then we're going to do plus 400 tan of x. Oops, I did 440. 400 still gets a little crazy. Don't look at it yet. It's not what we need yet. Just x, and then -7. Okay, so let's see what we're looking for here. And let's make sure I'm in degree mode. Did I do that yet? No, I didn't. Okay, there we go. Now we're in degree mode, so life makes a lot more sense. Do make sure you put the Desmos in degree mode when you're using this. Okay, so do you see right here, at this angle, this would be exactly 10. So we want our launch angle to be greater than this. Okay, so I'm going to move this guy up here so I can go snip all of it together, and we'll put that in our notes. Edit, copy, paste it in. Oops. Okay, so here's what we just worked on. Move it down here so we can see it. Shrink it a little bit. All right, so that's how we find the solution to this. We're not going to do it algebraically. We're going to do it graphically. But this graph is all we need. It tells us that that launch angle needs to be greater than 19.385, and that's degrees. All right, so that is how you do number 1. Okay, let's take a look at number 2 now, and I'll walk you through that one. Okay, so for number 2, it says a quarterback in a football team releases a pass at a height of 6 feet above the playing field. The football is caught by the receiver at a height of 4 feet, 90 feet directly downfield. The pass is released at an angle of 35 degrees with a horizontal. All right, so let's snag this, and we'll start a new one. Okay, so the first thing we want to do is we want to set up our parametric equations. So, horizontal x with respect to time is, all right, oh no, I don't see anywhere in here where it tells us V naught. We don't have V naught. All right, so V naught, but we do have the angle this time, so we can do cosine of 35 times t. All right, and then the height with respect to time would be modeled by this, negative 16t squared, because we're dealing with feet again. Once again, still don't have that initial, but we do have the angle. All right, and let's see, the pass is released at a height of 6 feet. So plus 6. It is released at a height of 6 feet. Okay, so we're asked to find the speed at which the football was released. We need to solve for V naught. Well, they tell us that this ball was caught 90 feet directly downfield. That's at horizontal distance. So in part B, what I can do is say 90 equals V naught cosine of 35 degrees times time. Okay, so V naught, if I solve for V naught here, I come up with this, 90 divided by cosine of 35 degrees times t. Now, the next thing, we do know the height at which this ball was caught. The height at which it's caught is 4. So I know this, the height with respect to a time when it's caught. It's caught 90 feet. Here's the height. So I just figured out the time that it takes to go 90 feet. I know the height at which it is caught at 90 feet. And if I plug this in, then I can solve for time. I know V naught can be represented by 90 divided by cosine of 35 times t. And then this was times sine of 35 times t plus 6. So let's clean this up a bit. If we notice, these t's are going to cancel. And sine of 35 over cosine of 35 is really just tangent of 35. So what we're left with is this equation. 4 equals negative 16t squared plus 90 tangent of 35. That's just times. 90 times tangent of 35 plus 6. Well, guys, we can punch this in our calculator and get a value. This is approximately 65.019. Oops, no it's not. I need to, this is going to be 69. There we go. And then we move it over and subtract 4 from that, and that's where the 65 comes from. So all of this is 69.015, so you subtract it over, and you get negative 65.019 is approximately equal to negative 16t squared. You would divide by negative 16, and then you would take the square root. Okay, so what that tells me is the ball was caught approximately 2.016 seconds later. This is when the ball was caught. So now that we know when the ball is caught, we can plug that back in to find the initial velocity. We know the time at which it's caught. Now we can find the initial velocity. So I'm still working on B over here. Still working on B. B continued. All right, so what I would do is that initial velocity is equal to 90 over cosine of 35 degrees times the time, 2.016. And this gives us an initial velocity of approximately 54.5 feet per second. All right, part C, find the max height of the football and the time at which it reaches its height. That one we've done before. All you have to do is take that height equation, y of t, plug it in and find that max value, and then find the time at that max value. Part D, find the time after the quarterback releases the ball until the receiver makes the catch downfield. Now that we have the other piece of the equation, we can find that as well. So give these a try. I'll be here if you have questions, and look forward to hearing from you.